So an Eulerian trail was a walk that used every edge exactly once. There is a corresponding notion when it comes to vertices. Remember that a path was a walk that does not visit any vertex more than once, except perhaps to come back to where it started. So just as an Eulerian trail is a walk that traverses every edge exactly once, we can define a Hamiltonian path to be a path that visits every vertex exactly once, except perhaps if it's a cycle and it comes back to where it starts. That's the only time a Hamiltonian path is allowed to visit the same vertex twice. If a Hamiltonian path is also a cycle, we can call it either a Hamiltonian cycle or a Hamiltonian circuit. So that would have to be a walk which visits every vertex exactly once, except it does come back to where it began. If a graph has a Hamiltonian path, we call it a Hamiltonian graph. We stated a simple theorem in the previous video that characterizes which graphs are Eulerian. A connected graph which has 0 vertices of odd degree admits an Eulerian circuit, and a connected graph that has 2 vertices of odd degree admits an Eulerian trail, but not an Eulerian circuit. That was a nice theorem, and you can just look at a connected graph, look at the degrees of the vertices, and immediately know the result. However, there is not a similar known theorem for characterizing Hamiltonian graphs. Somehow constructing walks that visit every vertex exactly once is a lot trickier than a walk that visits every edge exactly once. All we're going to do is do our best to find Hamiltonian paths. Here's an example. The following graph that will appear momentarily is Hamiltonian, and we will find the Hamiltonian path. Okay, here's the graph. The goal is, can you find something that visits every vertex exactly once? Well, let's just start here, then move there, to there, to there, and you can kind of see where this is going now. And finally, we end over there. So we were able to trace out, starting from here, just go around like this and visit every vertex exactly once. Notice we didn't use every edge. This edge here was never used, this edge here was never used, because we just went around in this sort of snake pattern, but that doesn't matter. Okay, Hamiltonian just requires you to visit every vertex once, and it doesn't really care about do you use all the edges. There's not, however, a Hamiltonian circuit possible, which you can see, again, from this vertex of degree 1. If it's a circuit, okay, if I leave here, I would end up at this vertex. If I wanted to come back here, I'd have to pass back through this vertex. So a Hamiltonian circuit couldn't begin and end at this vertex here. Why couldn't it begin and end anywhere else? Again, this vertex of degree 1 presents a problem. If it's in the middle of the path, the only place it could have come from is here. But if it's in the middle, then I have to leave and I'd have to go back here, and I am not allowed to repeat vertices that are not the start and finish in any Hamiltonian walk. Okay, so vertices of degree 1, just as in the Eulerian case, can be very handy in analyzing graphs. Okay, so any Hamiltonian path can't visit this in the middle. It also can't start and stop there. Therefore, there can't be a Hamiltonian path on this graph. Okay, let's take a look at another example. Here's a graph. Let's actually trace out a Hamiltonian path. All right, let's start over here, move to this vertex, to this one, to this one, to this one, over here, down here, here. And now we could actually pop right back here and end up where we started. So since we can extend that to a Hamiltonian circuit, that's great. This is a Hamiltonian graph. Okay, another example. The following graph is not Hamiltonian. Here it is. So can you try to piece together a convincing argument that it's not possible on this graph to make a walk that visits every vertex exactly once, except perhaps coming back to where it started? Well, any vertex of degree 1, we've already remarked, can't be in the middle of a Hamiltonian path. If a vertex of degree 1 was in the middle, I'd have to enter it and then go back, but since it's of degree 1, there's only one edge connected to it, so I'd have to use the same vertex twice. So any vertex of degree 1 cannot be in the middle of a Hamiltonian path. Here we have 2 vertices of degree 1, however. So that's not an immediate disqualification. Okay, I could have one of these vertices at the beginning and one of them at the end. Okay, so whether I start here and end here, let's suppose that there is a Hamiltonian path. The two vertices of degree 1 have to be the start and the finish. So either I start here and end here, or the other way around. But either way, I'm going to end up at this vertex, this sort of central node, somewhere in the middle. Once we're in this central node, if I do this loop, I come back to the central node. So I can't have this as some sort of intermediate vertex because I would necessarily trace out this triangle and end up back where I started. So either I start here, in which case I have to hit this node next, and either I just miss that and I don't hit these vertices at all, or I do this loop and now I have to repeat this one. And similarly, if I start from this vertex, there's really no choice but to end up here, and then you have the same problem. Okay, so either you do the upper loop, in which case you use that central node twice, or you don't do the upper loop, in which case you're not visiting every vertex. Either way, there is no way to draw a Hamiltonian path on this graph. Related to the notion of Hamiltonian graphs is something called the traveling salesman problem. Suppose you're a traveling salesman and you want to visit various cities. You need to go sell your vacuum cleaners in, Sheboygan, but you also need to sell them in Fort Worth. But traveling between cities costs money, as it does. So given a list of cities and various costs associated to going from one city to the next, can you find a route that visits every city exactly once because you don't want to repeat yourself, okay, but minimizes travel costs because you want to make the most money possible? Also, you want to return to the city that you started at because you do live somewhere, even if you are a traveling salesman. So the cities can be thought of as vertices, routes between cities are edges, and costs of traveling from one city to another are weights on the edges. So what we're trying to do is construct a Hamiltonian circuit. In other words, visit every vertex, exactly once, except to come back where you started. And you want to use the smallest weights possible. You want to use the minimal cost. Some graphs, however, are not Hamiltonian. So this problem might not have a solution. But in theory, one can travel from one city to another at some cost. So even though there are ways to construct graphs that are not Hamiltonian, in this problem we'd actually be dealing with a complete graph. Any two cities, it's possible to go directly from one to the other, even if it's ridiculously expensive. So you can always think of there being an edge between any two cities that you need to visit. It might just have a very high cost on it. So since we can travel from any vertex to any other, there's actually a lot of Hamiltonian circuits. On a complete graph, remember, any two vertices are connected. So if you want to go from vertex 1 to 2 to 3 and then end up at vertex n and then go back to vertex 1, it's possible. There are all of those edges in the graph. But you could also go from vertex 1 to 3 to 5, back to 2, then to 4, then to 6, whatever. Any vertex is always an option. So any permutation of the vertices is a possible path. And there's lots of permutations of the vertices. If there are n vertices, there's n factorial possible ways to list them out. And since all edges exist, they're all possible Hamiltonian circuits. So if you have a complete graph on n vertices, there are in fact n factorial different Hamiltonian circuits. That's a lot. Can you find the one that minimizes the cost without actually listing out all possible paths, computing all of their possible costs, and finding the smallest one? While it's computationally possible, if you have a lot of vertices, n factorial is a very, very large number, and it might not be feasible to actually compute all of the paths and all of their costs. So is there a way to find the minimal cost path that's faster than just finding all of the paths and computing all of the costs? So as an example, let's suppose we need to find the Hamiltonian circuit of smallest possible cost that begins and ends in Denver in this travel map. So we live in Denver, we need to visit these 5 other cities. It doesn't really matter what order we do it in, but we just want to visit each one of them once. And we need to find the cheapest way to make that happen. Now this is actually a complete graph. Any two cities you look at, there is an edge directly connecting them with a cost associated to it. We have to begin and end in Denver, but since the graph is complete, we can actually go in any order we want. If you want to go Denver, Seattle, all the way to New York, then back to Chicago, it's doable. That edge exists, but that's a very expensive flight. Okay, notice that going from Seattle to New York is $550, which is more expensive than Seattle to Chicago for $200, then Chicago to New York for $100. So not every edge really makes sense, but at least they all exist, which means every possible ordering of cities is a legitimate path we could take. Since we have to begin and end in Denver, there's 5 other cities that we need to list out, so there's 5 factorial or 120 possibilities. You could compute them all. So for example, we could say Denver, Seattle, LA, Houston, New York, Chicago, Denver. Denver to Seattle is 180, Seattle to LA is 210, so far we have $390. LA to Houston is 250, so 390 plus 250 is $640. Houston to New York is 140, so now we're at $780. New York to Chicago is 100, so that's $880. Chicago to Denver, another 220, so now we are at $1,100 total. For every possible path, you can compute the total cost. But what if there was a single additional city? Then instead of 5 factorial or 120 possibilities, there'd be 6 factorial or 720 possibilities. One more city would then create 7 factorial, which is close to 5,000. Okay, so these, as the number of cities goes up, as the number of vertices goes up, the number of possible paths you have to compute increases extremely rapidly. It's actually doable for 120 paths. You could do it in reasonable time, especially with the aid of a computer. But as the number of cities goes up, even a computer is not going to be able to keep up with the vast increase in computational complexity. If you could find an algorithm, in other words, just an explicit list of steps to feed into a computer that can solve this problem in a faster way than just listing out all possible solutions, that would be really great. This is known as the traveling salesman problem, and it's recognized to be an extremely difficult problem. Can you find an algorithm that efficiently finds the best solution to this problem in general? And it's a big deal in computer science.